Okay, so now let's talk about chemical change as opposed to physical change. When you have a chemical change, you actually make something entirely new, which differs from whatever original things you had in composition and in chemical and in physical properties. So an example of this is salt. We all know table salt. We've all put it on our food at some point. But this is what sodium looks like, and this is what chlorine looks like. Sodium is this shiny metal that oxidizes really quickly, making this white layer on the outside. So if we ever get sodium metal in its pure form, we have to keep it under oil. And chlorine gas we have to keep bottled in a jar because it's highly dangerous and can kill us. And you can see it's this yellowy color. So can you see this and this look nothing like the salt, the table salt, okay? So there's clearly been a chemical change. If I mix the sodium and the chlorine, I get out sodium chloride. And all of these three things look completely different. So the chemical change has made this sodium chloride, and this is a completely different composition to the sodium and the chlorine. And this has got completely different properties. If I put this in water, it's just going to dissolve. If I put this in water, we will have a small fire. So when we talk about chemical change, this is what the main object of looking at this is. Chemical change has two main types of reactions that we need to know, and they are a synthesis reaction and a decomposition reaction, okay? So in synthesis, you have two or more things combining to form fewer substances. So if you synthesize something, if you create something, you take lots of little things and make fewer end products. So lots of reactants, few products. A decomposition is the opposite, when you take one large single molecule and you break it down into lots of smaller, simpler molecules. So we talked about this, we talked about the decomposition of water by electrolysis when we looked at the previous topic. So a decomposition reaction takes a single compound and breaks it into simpler substances. You can think about this, if you want a way to remember this, you can think of a great big dead buffalo lying in the bush, and as the big dead buffalo decomposes, it breaks up into millions of tiny little bits and pieces that the bacteria carry off. So you started with one big thing and ended up with lots of little smaller, simpler things. Okay, so what also do we know about chemical change? It is going to use large amounts of energy. And this is relative to physical change. You need large amounts of energy because you are going to either break strong covalent bonds or break strong electrostatic forces. Because the rule of chemical change is bonds are broken, bonds are reformed. So in order for the reaction to occur, you have to break the bonds first, and this is where the energy goes. And any reaction that you see can be reversible, but usually they're not really reversible. Most of the chemistry we do, the reaction is not reversible, but they can be reversible. We deal a lot with that in grade 12, but they're not as reversible as a physical change. It's by no means as easy to take the products back to the reactants in a chemical reaction. So for instance here, let's have a look at the synthesis reaction. We have sodium plus chlorine going to sodium chloride because we had two things on the reactant side and we ended up with one thing on the product side. Now, I will say this a lot going forward, reactants go to products. This arrow is important. It tells you which direction the reaction is occurring. You always have to use an arrow when we talk about chemical change. And I always write reactants go to products. If the atoms are not on the left, the atoms cannot be on the right. Okay, so here are sodium atoms, here are chlorine atoms, here are sodium atoms and chlorine atoms. Yes, they have become ions on this side, but there's no all of a sudden carbon or oxygen or hydrogen in the sodium chloride because there weren't hydrogen or carbon or anything else on the other side. So the reactants go to products. And I know this may sound like I'm treating you like an idiot, but experience has told me I must be very careful explaining this, that if it's not on the left in the reactants, you cannot get it on the right on the products. Okay, if you find something in the products that's not in the reactants, that is now witchcraft. Okay, so here's another example, but this is now an example of a decomposition reaction. Remember we looked at this decomposition of water with electrolysis. Here are my little water molecules. See, one red oxygen, two little white hydrogens. And if we decompose them, we must put in a lot of energy. I showed you with the 9-volt battery. You take your water, put in some energy. So this is my reactant, and it goes to these two products. This is my hydrogen gas, and this is my oxygen gas. So the other thing we're going to look at is I've got 1, 2, 3, 4, 5, 6 atoms on the left. I've got 1, 2, 3, 4, 5, 6 atoms on the right. But the main point here is this is a decomposition reaction. So I took something that was a relatively complex molecule and I split it into more simple molecules. So complex reactants go to more simple products. So one of these splits up into two of those. I'm not talking about the balanced equation. I'm talking about how this H2O is one thing. Okay, this H2O is water, one substance, and here I have two substances, hydrogen and oxygen. Okay. So what happens in a chemical change that is different from a physical change? The chemical composition is changing. Okay. The bonds, the chemical bonds are broken and the atoms and the ions are rearranged. So look back here quickly. I had H2O and it went to H2 and O2. We have broken these bonds over here and then they have reformed differently. That is how the chemical reaction has gone. Chemical bonds are broken, the chemical composition changes. But what you have to remember is the number of atoms is going to stay the same. The number of atoms, now be very careful with your definitions here, the number of atoms in the reactants is the same as the number of atoms in the product. But we can have different numbers of molecules. Okay, look over here. I've got 1, 2 molecules on the left and I've got 1, 2, 3 molecules on the right. If I was just, for instance, turning this water vapor into, for instance, this water liquid into steam, I would have the same exact number and composition of everything, whereas in a chemical change, the bonds are broken, bonds are formed, and the number of molecules can change. So before the reaction is complete, new chemical bonds are formed, and this means new substances are formed. Okay, so to summarize, in a chemical change, there's a change in the size of the molecules, but not the atoms. If you're a hydrogen atom at the beginning, you're still a hydrogen atom at the end, but you might have been a hydrogen atom bonded to an oxygen, and now you're a hydrogen atom bonded to another hydrogen atom. Okay, so during a chemical change, there's a change in the size of the molecules, but not the individual atoms. There's a change in the shape of the molecules, but not the individual atoms. And there is a change in the number of the molecules, but not the individual atoms. This is why you must be very clear in your head, which is why we look at all of those diagrams, like the ball and stick diagrams, and why you have to draw little ball pictures so that you understand that what is the difference between an atom and a molecule, so that you can understand this, that the number of molecules is changing, but the atoms are not changing. Okay, now this page is quite important, so you should think about this page. If a chemical reaction occurs, we can often observe a change. These are the various changes that you can get. Bubbles of a gas can form. This is often called effervescence. Okay, this is the proper word for bubbles forming. Usually the bubbles are carbon dioxide, but not necessarily. So bubbles form. A color change can occur, and this color change can be very different to the physical color change. This is very important. The temperature of the reaction mix changes. And then if we have, for instance, bubbles forming, the mass of the reaction mix can decrease because the bubbles of gas are coming off and making the thing lighter. Or a precipitate can form. So I'm not sure if you're familiar with this word precipitate, but a precipitate is a little bit of a solid suspended in a liquid. So sometimes precipitates form when you mix two liquids together and then all of a sudden they become cloudy. Like for instance the test for carbon dioxide. When that mixture becomes cloudy, in chemistry we say a precipitate is forming. So here are two examples. Okay, this is lead iodide, I think. If you look in the syringe, you can see this, the eyedropper, not the syringe. If you look in this eyedropper, it's colorless inside there, and if you look in here, it's colorless inside here. But when these two colorless solutions mix, you end up with a small yellow solid forming inside there. Here's a similar thing. If you take this slightly cloudy solution and you mix it in this clear solution, here is a precipitate forming as well. This is a white precipitate. This is obviously a yellow precipitate. So a precipitate is a solid suspended in a liquid. Okay. And there are two main types of reactions. If we look back at the other slide tells you that the temperature, if a chemical reaction occurs, we can often observe a change. The temperature of the reaction mix changes. Okay, to discuss this, we have to look at these two things. These are two terms we're going to be using a lot moving onwards, so you need to memorize them and memorize the difference. So in an endothermic reaction, energy is absorbed during the reaction, and in an exothermic reaction, energy is released during the reaction. So fairly obviously here you can see a fire. This is an exothermic reaction. Other things that are common exothermic reactions, for instance, if you hold a handful of washing powder and you put your hand in water and you shake it around, you will feel as the washing powder dissolves, your hand gets hot. That's an exothermic reaction. Very few reactions are endothermic, but sometimes, I don't know if you've seen those ice packs that you can get in emergency first aid kits, and you snap the ice pack and they suddenly get cold. That will be an endothermic reaction that you can look at. Okay, and this is where I'm going to stop here for now.